Module 2, Session 2. Session 2 will cover Learning Outcomes 4.2.3 to 4.2.5, Scatter plots. Learning Outcomes 4.2.3 to 4.2.5, Scatter plots. In this section, students need to begin by understanding what bivariate data is. Remember that bi comes from the Latin for two. A helpful method for explaining this is to compare a dataset of univariate data, for example, the heights of everyone in the class, to a bivariate dataset, for example, the heights and the weights of everyone in the class. There will be a pair of values for each student in the class. Guide students to understand that the two bits of data belong to one individual. For example, Lindelani, 1.72 meters, 74 kilograms, and Naledi, 1.65 meters, 58 kilograms. Plotting scatter plots is revision of plotting points on the Cartesian plane from previous levels. Let's work through the steps using an example of plotting newborn babies' ACBAR scores against the baby's health scores at 3 months. An ACBAR score is a measure of a newborn infant's physical condition used in hospitals. Step 1. Draw and label the axes. The independent variable goes on the x-axis and the dependent variable on the y-axis. In this case, the ACBAR score is independent and the 3-month score is dependent. Step 2. Choose an appropriate scale for the axes. Look for the minimum and maximum values and then number the axes so that all the values fit. Both scores have a set range of 1 to 10, so the axes can go up to 10. Step 3. Plot a point for each pair of values. Each point represents the data for one baby. The completed scatter plot gives a visual impression of how the two variables are related to each other. For example, in our baby's health scores example, we can see a definite pattern between the variables. They seem to lie along an increasing straight line. This tells us that there is a positive linear correlation between the two variables. It means that the baby's 3-month health score is likely to be higher if the ACBAR score was high too. Let's look at more examples. Some scatter plots might reveal a completely random pattern between the two variables. In this case, there is no correlation between the variables. A positive linear correlation means that as one variable increases, the other variable also increases in a linear fashion. A negative linear correlation means that as the independent variable increases, the dependent variable decreases in a linear fashion. We can also see that sometimes the relationship between the variables is not linear, and we can fit other functions to the relationship. An exponential growth graph shows that as the x variable increases, the y variable increases exponentially. In other words, they show compound growth. A negative exponential graph shows that as the x variable increases, the y values decrease exponentially. This is a decay curve and shows compound decrease. We might even see the variables that show a quadratic function pattern with either a maximum or a minimum value. Students should be able to recognize these patterns and describe them intuitively. Students need to be able to draw in a line of best fit for all the points on a scatter plot. This can be difficult because students tend to feel that some of the points must be right, and therefore they want to connect the points. Explain to the students that all the points are the correct data, and that the line they draw needs to represent all the points equally. It is quite possible that the line of best fit does not touch any of the points. Roughly the same number of points should lie above and below the line. Teaching tips. Give students some strategies for drawing a line, so that they can follow these steps rather than trying to connect points. Here are some. It helps to use a transparent ruler so that you can see how many points lie above and below a line as you draw it. Also try to balance the distances between the line and the point on either side. Imagine drawing short vertical lines from the line to the point. The total sum of distances above should be the same as the sum of the distances below. You could try to take a long thin stick or a piece of dry spaghetti and try to place it to fit before you draw the line. Try to draw a rectangle that encloses all of the points. Then draw the line of best fit through the long axis on the rectangle right through the middle. Try to avoid drawing lines that have clusters of points at the ends of the lines. In this case, B is a better line as it breaks up these clusters. We also need to know how strong the predictive power of these lines is. This is called the strength of correlation. We can judge the strength of correlation visually. If the points fit exactly on the line or curve of best fit, whether it is positive or negative, it is called a perfect correlation. This is very rare. If there is a strong correlation, the points are clustered very closely around and on the line of best fit. For a weak correlation, the points are scattered around the line randomly and it is more difficult to make out the pattern of correlation. And, as we have already seen, if the points are randomly scattered and don't form a distinct pattern, then there is no correlation between the two variables. Let's watch a lecturer drawing a scatter plot.
Draw an intuitive line of best fit for the following relationship. So in this table, as we can see, we actually have two variables which exist, which form a relationship between x and y. So the variable is x, which of course controls the process, and the one which depends on x is y. So x is the independent variable here, so which means that this relationship is controlled by x. All we have to do is to draw a line of best fit for this relationship. Now, the first thing we need to understand here is how are the values of x and y distributed within the Cartesian plane. You will see that the x values are all positive, the y values are all positive, which means that your graph must look something similar to this. It can look something similar to this. It is not necessarily required for you to have extensive x values in terms of the negatives, as well as y values in terms of the negatives. And the reason for that is what I explained previously, just a short while ago. Your origin is always where the two lines meet. The next thing you need to do, you need to evenly distribute the scale of your units. So you must start with the x-axis. You can see that the smallest value is 0, the highest is 3.5. You need to fit that all of here. So my suggestion would then be 1 here, 2 here, 3 here. You might need to extend that because you go until 3.5, which means that you can just go a bit further. You can go just a bit further until 4. So which means that your 4 can be around here. What have we done here? We have formed our values of x in terms of units increasing by 1. And that can also happen in terms of your y values. You can use units of 2s, you can use different units compared to your x units. That's not a problem. So you can start saying this is 2, this is 4, this is 6. Alternatively, you can say 1.5, 3, 4.5, and then 6. So you're using different units going up here. It all depends on how comfortable you are with these values. So here we can use the same units. We can use the same units, but in shorter version. I'm going to demonstrate now why I decided to erase this. I'm going to demonstrate now why I decided to erase this. Here I'm using units of 1.5. Here I'm going to use units of 1. So here I've decided to use units of 1 on the x-axis. 1, 2, 3, 4, 5. And then here I've used 1.5, 3, 4.5, 6. But whatever unit you are using, it must be consistent. The next thing you need to do, you need to plot these points or the coordinates. Starting off, of course, by labeling that these are my x-axis, these are my y-axis. You start off with the x value, x and 1. When x is 0, the y value is 1, which is something about here. So you have a dot here. When x is 0.5, the y value is 1.2. 0.5 is between 0 and 1. You're looking at 1.2, which is something close to here. When x is 1.5, when x is 1, y is 1. So you have 1 and 1, which is something around here. And then x, so this is done, this is done, this is done. X is 1.5, between 1 and 2, y is 1.8. Looking at 1.8 around here. That is done. 2 and 2. X is 2, y is 2, just above 1.8. X is 2.5, y is 3. 2.5 between 2 and 3, and then y is 3. 3 is about here. And then x is 3, y is 4. X is 3, here is 3, y is 4, 4 is about here. X is 3.5, y is 6. 3.5 is between 4 and 3, or 3 and 4, and 6 is about here. Okay, now you can see that this is definitely not a straight line, it's a curve. But the outcome of that is that whatever you're trying to plot, you must make sure that you follow a smooth trend which connects almost your first and your last line, almost. So you must start where the graph begins, adjusting the distance between. If you decide to go in between here, then you adjust the distance between this point and that point, which looks something similar like this. But you must cover a relative number of your points. You're looking at something like this. So this is the line of best fit. You can see that you have some lines started being at you've touched this line, you went out of that. This was almost an outlier, it was out of your region, but you managed to get close to that. You did definitely get this point. You were just close to that. You were just close to that. You got that point. So you have drawn a line of best fit, and this line of best fit forms almost an exponential curve of some sort.
In the next session, we are going to cover least squares regression analysis. In your groups, have a discussion on your approach to teaching this topic and how you explain its practical application to students.